In this lab, I will verify DeMorgan's law and I will implement boolean expressions on proteus. Today we will discuss about DeMorgan's law. So here you can see is an example of DeMorgan's law. The bar on top of a plus b plus c can be put on these variables separately by simply changing the gate from AND to OR and in below from OR to AND. We just have to simply switch the gate from OR to AND 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 to OR, and then we can separate the bars. And here you can see it is a truth table which verifies that x plus y whole bar is equal to x bar and y bar. The truth table, you can see the outputs are same for both. Now here we have implemented the circuit for it. There is a small mistake in this circuit. I have put the gates on the wrong position. The AND gate is over there on the upper side and the OR gate is for x plus y whole bar. So now the circuit is complete. So now you will verify the truth table. First we will run the simulation. And then as you can see, for the input 0 0 the output is 1 1. The input 0 0 the output is 1 1 for both of them, and for all the other combinations the output will be 0 0. The outputs are coming same for both the functions, so it verifies DeMorgan's law. Now we will verify it using another example. In this example, we have taken x and y whole bar and changed into x bar plus y bar. So the circuit is here on your screen. Now we will check the different input combinations and verify the truth table. For the input 0 0, the output is 1 1. In this lab number 4, I will implement the given Boolean expression on proteus. These are the two functions that I have to implement on proteus. So first of all, we have to see how many inputs we have to give. So here are 4 inputs, A, B, C and D, and the gates that we are using are AND, OR and NOT. So first we will place the logic toggles, which are basically the inputs. So there are 4 inputs, A, B, C and D, and then for the first expression we are using A naught and C naught. So we will connect NOT gates for A naught and for C naught. And then after that we have to place an AND gate which will have the inputs A naught and B, and another AND gate that will have the inputs C naught and D. After this we have to simply OR the output of these two gates. So this is our Boolean expression implemented on proteus. We will just place a logic probe at the output to check the output. So it's working. So for the second expression we have to use A naught, B naught, C naught and D naught. So again we will put all the inputs using logic toggles, and as we are going to use the NOT of all these inputs, we will simply place NOT gate in front of all these inputs. Now we have to AND A naught B naught and C naught and D naught. Then we will simply OR the output of these two AND gates. Now the implementation of the second Boolean expression is also complete. We can run it. You can see it's working. Now our next step is to make a truth table. So the truth table is already made over here. As you can see on your screen, A, B, C and D are the 4 inputs, and then in the function 1 we had used not of A and not of C. So we have made the possible combinations of not of A and not of C. Then we have used an AND gate for A naught and B and another AND gate for C naught and D. At the end we used these two inputs for the OR gate, and then our final result is mentioned over here. This was the final output of our function. So we will verify it on Proteus. For all the input 0, the output is 0. Now for all of the input 0, the output as you can see is 0. And then for the input 0 0 0 1, the output is 1. As you can see, the output is 1. So this verifies our truth table, and it also verifies that the circuit that we have made over here in Proteus is working fine.